Hi there, and welcome to another tutorial for the Edexcel Further Pure 1 Maths course. This is the third tutorial on proof by induction, and it's about recurrence relations. As always, the Edexcel syllabus, we take a look. We've done summing series, we've done divisibility. Now we want to be able to find the general terms in a recurrence relationship sequence. For example, if u to subscript n plus 1 is 3, u subscript n plus 4, and u1 is 4, prove that the general term un is 3 to the n minus 2. Okay, we're going to start straight off with that example. I'm going to take you through the inductive process. Just before I do that, just in case you're not sure what recurrence relations are, this tells you the next term in the sequence is the previous term times 3 add 4. You get your answer for that, and that's your second term in the sequence. To get your third term, you do 3 times the second term plus 4, and that's your third. To get your fourth, you do 3 times the third term plus 4, etc. Now, this is the relationship, okay, and we want to show that the general term, the nth term, is given by this formula here. So before we launch into it, let's just see what is going on with this sequence. If u1 is 1, okay, we could actually get our calculator to do this for us nice and neatly. Let's bring our calculator over here. Okay, so we are trying to work out 3 times u1 plus 1. So 1, that's our answer. So we do 3 times aunts plus 4. u2 is 7. We could just use our calculator here and press equals again. u3 is 25. And we could do it one more time here, and we could just say equals again, 79. So u4 is 79. In general, we want to show that the nth term, okay, is 3 to the power of n subtract 2. Now, was that working here? The first term was 3 to the power of 1 subtract 2, which is 1, correct? Was it working here? 3 to the power of 2 subtract 2 equals 7, it worked. The next one would be 3 to the power of 3 subtract 2, which would be 25. And the next one would be 3 to the power of 4, which is 81, subtract 2, which is 79. It looks like this is working. However, what we learned in the first video about Mersenne primes, we can't be sure if this formula always works. We need to prove it, and we're going to use induction. Okay, let's use our induction. Step 1, and we're going to state our proposition. Our proposition is simply that u subscript n is 3 to the power of n minus 2 for n bigger than or equal to 1. The next stage is the basis case, and we are checking this statement is true when n equals 1. Now we are told u1 is equal to 1, but on the other hand, u1 using this here would be 3 to the 1 subtract 2, which again is 1. And therefore, we know that this formula here works for n equals 1. So therefore, true for n equal 1. Now, the third stage. This is our assumption stage, as always. We're going to assume that this formula is true for n equals k. So assume true for n equal k. And we're going to write down what that means, i.e. that u subscript k is equal to 3 to the k minus 2. So we've done nothing really hard here so far. The next step, the hard step, is the inductive step. Now, as always, this is not part of your proof. This is just something you might write on a scrap of paper to show you where you're trying to aim at. You are trying to show, not write down, but show, using this knowledge here, that u to the k plus 1 is 3 to the k plus 1 minus 2. That's what you're trying to show. If you can show that using this knowledge, then you have done the right thing. Okay, so let's move on. We want to, in the next step, do the inductive step, which is step 4. and we want to work out what u to the k plus 1 is. We can't use this formula for it. We cannot use that formula. That's what we're trying to show. What we can say, though, is a fact we do know is u to the k plus 1 is 3 lots of the term before it, uk, plus 4. But we know what uk is from our assumption step. uk is 3 to the k minus 2. So we can write this as 3 times 3 to the k minus 2, and that is by our assumption in step 3. And then we can expand this. 3 times 3k is 3 to the k plus 1. 3 times minus 2 is minus 6, and then plus 4 would be minus 2. And look what we've shown. We have shown that u to the k plus 1 is the thing we were trying to show, is 3 to the k plus 1 minus 2. So we have proved that therefore this is true for n equal k plus 1. And we've done the hardest bit. The last bit, therefore, step 5, is just to simply conclude. So we write our conclusion, and we write true for n equal k, then true for n equal k plus 1, since true for n equal 1, we know that un equals 3 to the n minus 2 is true for all n bigger than or equal to 1, and we're done. And that's all there is to that. I would like you to try an example very similar now. Here's your turn. Pause the video, work through this proof by induction, and then we will go through the answers in 10 seconds. Okay, step 1 as always is the proposition. And our proposition is that un is equal to 3 to the power of n minus 1 over 2 for n bigger than or equal to 1. Step 2 is the basis case. We want to check this is true for n equal 1. So we let n equal 1. We know on the one hand that u1 is equal to 1, but on the other hand u1 is 3 to the power of 1 minus 1 over 2, which again is 1. So we know that it's true in the case n is 1, so we can write therefore true for n equal 1. Third stage is our assumption stage with assumption. So what we're going to do here is we're going to assume the proposition is true for n equal k, so that would mean this formula is true when n is k. You're substituting k for n, so you're going to say that therefore uk is equal to 3 to the k minus 1 over 2. And you haven't done anything particularly hard so far. Now this is where it gets a bit trickier. Or on a separate piece of paper or on a scrap of paper, do not write this in your proof. What are you trying to show? Knowing these three things hold here, and in particular the assumption stage, you want to show that u to the k plus 1 is 3 to the k plus 1 minus 1 over 2. That's what you want to show. You can't write it down straight away. You're going to have to use the recurrence relation somehow and this assumption to prove that is true. So that's where we're trying to get to. Okay, let's move on to the hard part then, this inductive step. Step 4, inductive step. Well, you want to work out what u to the k plus 1 is. You can't use this. What you can say is that it's equal to 3 to the uk plus 1. And you know a formula for this from the previous slide. uk is 3k minus 1 over 2. So what you can do is you can say 3 to the k minus 1 over 2 plus 1. You've substituted for u to the k using your assumption step, step 3. Then you can multiply this out. That would be 3 to the k plus 1 minus 3 over 2 plus 1, just timesing the 3 out. And then what you could do is you could effectively divide out the half. Or I could make that, to add these, I'll make them both over a common denominator. So that's 3 to the k plus 1 minus 3 over 2 plus 1 over 2. Sorry, plus 2 over 2, even, plus 2 over 2. So that's 3 to the k plus 1. Minus 3 plus 2 is minus 1 all over 2. And look, you've shown what you wanted to show. Remember, you wanted to show u to the k plus 1 is 3 to the k plus 1 minus 1 over 2. Well, you've done that now. So therefore you can say true for n equal k plus 1. Just to take it home then and finish it on step 5. Step 5 is your conclusion step. And as always, you just state true for n equal k, then true for n equal k plus 1. You've shown that since true for n equal 1, you've now shown that un is in fact equal to 3 to the n minus 1 over 2 for all n bigger than or equal to 1, and you're done. And that's virtually all you need to know for this. I just think I need to show you one more example where it can get slightly more complicated. By all means, as I turn to this next slide, if you think you can proceed and do it on your own, do so. Otherwise, just have a look, copy down the notes and make sure you understand a slightly more complicated example. Here's that example. Work through if you feel you can, otherwise let's work through it together. I call this the double assumption example. It says, given that u subscript n plus 2 is equal to 5u subscript n plus 1 minus 6u subscript n, with u1 is 13 and u2 is 35, prove by induction that un is given by that formula there. Now the slight difficulty here is that this term here, this un plus 2, depends on two previous terms. So, for example, in your basis case, to show this is true for the case u1, you need two previous terms in order to show this is true in your induction. So let's go through bit by bit and just see where it gets more complicated. Firstly, your proposition, where your proposition is easy. Your proposition is simply that un is equal to 2 to the n plus 1 plus 3 to the n plus 1. And for n bigger than or equal to 1. Now your basis, that's step 1. Your basis case is slightly different here. Now let's just see why. In order for anything to be true for u to the n plus 1, it's got to be true for the two terms before it. Okay, so in your basis case, you've got to check it's true for two terms in order for it to be true for the subsequent terms after that. It's kind of like in your dominoes, the two first ones are kind of, both of them depend on the others falling. So both of these have to fall to make everything else fall afterwards. Okay, so that's where it's slightly different. You need to check both cases because you're going to rely on two terms to check the term after those two actually works. So the basis case is both n is 1 and n is 2. Now you know that u1 is 13, and you also know that u1 by that formula is 2 to the power of 2 plus 3 to the power of 2, which is 13. So you're done. You know that u2 is given to you is 35, and you know from the recurrence from this here that u2 is equal to 2 to the power of 3 plus 3 to the power of 3, which is 8 plus 27, which is 35. So you know it's true for n equals 1 and n equals 2. Okay, now we're going to move on to the assumption stage. You're going to assume this thing is true for n is equal to k and n equals k plus 1, because we're trying to show it's true for maybe k plus 2 here in the future, so we've got to assume it's true for the previous two ones using our relation, i.e. we know that uk is 2 to the k plus 1 plus 3 to the k plus 1, and we're going to know that uk plus 1 is 2 to the k plus 2 plus 3 to the k plus 2. So we have to show it's true. We have to assume it's true for the two previous terms so that we can show it's true for the next term after. What we are going to try and show in our inductive step, we're going to try and show that u to the k plus 2 is 2 to the k plus 3, sticking in k plus 2 here, plus 3 to the k plus 3. If we can show that, then we're done. Okay, so that's what we're going to try and show. That's not part of our proof, that is our aim. That tricky inductive step here. So step 4, the inductive step. We want to work out what happens for uk plus 2. Now we know that's equal to 5 u to the k plus 1 minus 6 u to the k, and we know something is true about u to the k plus 1 and u to the k. We know u to the k plus 1 is 2 to the k plus 2 plus 3 to the k plus 2, and uk is 2 to the k plus 1 plus 3 to the k plus 1. So we can substitute in here 2 to the k plus 2 plus 3 to the k plus 2 minus 6, 2 to the k plus 1 plus 3 to the k plus 1. And that is by step 3, our inductive step. Okay, we've got 5 lots of 2 to the k plus 1. Oh, sorry, 2 to the k plus 2, and we've got 5 lots of 3 to the k plus 2. And we've got to subtract 6 lots of 2 to the k plus 1, subtract 6 lots of 3 to the k plus 1. Now, probably the easiest thing to do here is break this down into this here, this 6. You could break that down into 2 times 3, and that is 2 times 3. So you could add a power to each of these. So this would be 5 lots of 2 to the k plus 2 plus 5 lots of 3 to the k plus 2. And this would be minus, so that's 3 times 2. So that's minus 3 times 2 to the k plus 2. Bringing that 2 and times it in there. And this is 2 times 3. So this is minus 2 lots of 3 to the k plus 2. And we're nearly there. We've got 5 lots of 2 to the k plus 2 minus 3 lots of 2 to the k plus 2. So we've got 2 lots of 2 to the k plus 2. And we've got 5 lots of 3 to the k plus 2 minus 2 lots of 3 to the k plus 2, which is 2 lots of 3 to the k plus 2. And that's like 2 to the 1, and that's, sorry, that would be 3 lots. That's like 3 to the 1. So this would be 2 to the k plus 3 plus 3 to the k plus 3. And remember, that's what we were trying to show. U to the k plus 2 is 2 to the k plus 3 plus 3 to the k plus 3, and we've done it. So we can say, therefore, true for n equals k plus 2, assuming it was true for k and k plus 1. And that's it, we're pretty much done, apart from our conclusion, and our conclusion is always the same thing. We're saying true for n equals k, therefore true for n equal k plus 1. So it was true for n equals k and n equals k plus 1, so therefore true for n equals k plus 2. And as it was true for n equal 1 and n equals 2, therefore true for all n bigger than or equal to 1. And we're done. And that's probably as complicated as it can get with a double assumption. 2 things you need to assume are true to show that the next one after that is true. And that's all there is. So for further homework and study, I suggest you read chapter 6, page 130 to 132, and do exercise 6C, all the questions. and then tune in for the next video on induction, which will be induction on matrix multiplication. Thank you for watching this video.